Definite integrals. Objectives. By the end of this lesson, you should be able to understand the limits of Riemann sums are used to formally define the definite integral, understand the graphical representation of a definite integral, recognize and understand the notation of a definite integral, draw graphs of functions and evaluate definite integrals using geometry, know the properties of definite integrals, use the properties of definite integrals to evaluate other integrals, use symmetry when possible to simplify the calculation of definite integrals and even odd functions, understand and apply the comparison theorem for integrals. It's a lot of stuff. So let's get the first one. Riemann sum. Riemann sum is a rectangular approximation of the area bounded between the curve and the x-axis with the property that the width and height of each rectangle can vary. So what that means is this. Let's say I give you a function. Like that. Riemann sum is how we did in the previous lesson. We did right and left and midpoint approximation. Riemann sum is that, but with any approximation you want to use. So you can do left, you can do midpoint. That was more of a left also. Here's the midpoint. You could do something right there. You could do a big one. And that's kind of what Riemann sum is, right? Riemann sum, unlike we did last lesson, Riemann sum you can use any width and any height. And I could go positive. Last time we only had to do positive, now I could do positive, negative. It's just rectangles that are going to help us approximate the area underneath the curve. So you can have big rectangles, small rectangles, anytime you want. Riemann sum that says it doesn't matter. Any width, any height. It could be above, it could be positive, below. But Riemann sum is we're going to add all those to get an approximation for our area. Now let's talk about integrable. A function f of x is integrable over a of b if all the Riemann sums, not just the endpoints, midpoints, all of them, the big, small ones, all of them, approach the same limit as the width of the largest rectangle approaches 0. So they're saying, hey, as long as the width of the largest rectangle approaches 0, so for us that's kind of like this one right there, right? My width right there. If you take the limit as this guy gets smaller, so what does that mean? That means that on your rectangle here, we're gonna make that a small rectangle. We get so small till it almost gets to 0. So when we take our limit, we get smaller and smaller until our limit equals 0. And you can tell as you get smaller and smaller, you get better and better approximations. So when you take a limit, right? You can't actually go to 0 because there's no rectangle that's the width of 0. But if you take the limit as you go to 0, we're going to add up all those rectangles, right, with all their different heights. That's what this guy is. That's the height, right? The height here is just whatever f of whatever that value is. The height there is f of that value. Same thing there. Same thing right here. If you take the limit of all that and add up all those areas of all those rectangles, you should get the limit, which is the area underneath the curve. So that's a general formal definition of integrable. It means, hey, if you could do all that and they all go to the exact same number, then that's your curve. The definite integral of f of x over a to b is the limit of Riemann sums. So this is a notation for a definite integral. If you notice, it looks very similar to our non-definite or indefinite integral, right? But instead we have these a, b here, which we're going to learn later. It's called limits of integration. They're just going to be numbers. So all this means is this right here is telling you that, hey, the area into the curve from a to b, which are just numbers like 1 to 3, is equal to the limit of the Riemann sum, which is equal to sum L, which is just a number. That's all that means. So when you see this notation here, this definite integral, it's saying when we take the definite integral from a to b, we're going to find the area underneath that curve. And how do we do it? Well, it's just taking the Riemann sum. That's what we're actually doing, the limit of the Riemann sums. That should give us some number. Again, note, the way we read this is this. We read the integral of f from a to b, or the integral from a to b of f. Either way is fine. But that's integration, and that's a definite integral. You should get a number when you have a definite integral. Let's do a graphical representation of the definite integral and see what it says. So, side area. So remember, we're finding the area between the curve, right? So we're finding the area between these guys, this right here. And find the area of this guy. So if we were integrating this function from, let's say, 0 to 6 of f of x dx, a couple things happen here. So we consider the area above the x-axis, so this guy right here, to be positive, and we consider the area below the x-axis to be negative. That's when we do integration, that's how we consider it. So anything above the x-axis is positive, anything below the x-axis is negative. And let's say the area of this guy was like 10. Let's say the area of this guy was 3. Well, we consider a negative 3. So the integral from all this would just be 10 plus negative 3, or 7. And that's the way it's going to work. So you find the area of this stuff here, find the area of that stuff there. If it's below the x-axis, it's negative. If it's above, it's positive, right? And if I negative values, we should know just by looking at this that the positive side is way bigger than the negative side. So we know for sure the integral from 0 to 6 of f of x dx is going to be positive, right? It's just by the look of it. So it's always going to be the stuff above the x-axis. In this case, that's like orange, minus the stuff below the x-axis, which in this case would be red. And that's how you find the area, the shaded region between the graphs. So a quick little quick recap. Limit. The y value function approaches as we approach some x values, right? We know that. So it doesn't even matter if it's valid in or not. The limit is the y value we get to. Derivative is the slope of the tangent line, or the instantaneous rate of change, limited difference quotient. Indefinite integral is a general antiderivative, right? Indefinite integral is we get like with the integral of this guy. No limits, so we're gonna get we take the antiderivative. We go backwards essentially. Right, with the plus c. The definite integral is a sine underneath the curve, so this one we should get a value. So the definite integral is when it's like this. We're going from 0 to 3 of 2x plus 1. That should give us some number. So let's do an example. Let's calculate the definite integral of this by using interpretation of sine area. So this is using area. So the graph 2x minus 5, so we start at negative 5. Slope of 2 over 1. Something to this effect. Right? It crosses at 5 over 2. And we're going from 0 to 3. So from 0, that's 1, 2, 2.5, and 3. So something to that effect. Now we gotta find the area. Now if we're looking at this, remember the way the area works? Area of this guy right here would be negative, and the area of this guy right here would be positive. And this one area like we know how to do. It's like if we're in geometry. This is a triangle. Area of that triangle is we're starting at negative 5. So base 1/2 base times height. 1/2 5. My height here, it crosses at 5 over 2. If you're wondering how I got 5 over 2, I just set it equal to 0 to find my x-intercept. So that's where it crossed, 5 over 2. So in this case, I'm going to get 25 over 4. And that's going to be a negative value because it's below the x-axis. Now to get this one right here, it's a little tougher. Well, I know my x is 3. If you try to find the y value where it crosses, easiest thing to do is just plug it into the equation. So 1. That point is 3, 1. So my little triangle there, let me draw it right here real quick so you can see it. It goes from 5 over 2 to 3. So that's 0.5, 1/2. And my height went all the way to 3, 1. So 1. So I'm going to add that to my 1/2 base times height of the upper triangle. So I get negative 25 over 4 plus 1 over 4, which would get me negative 24 over 4, which would get me negative 6. So I know it's got a little messy right there, but it's basically find area of two triangles, is what it turned out to be. Area of this triangle below the x-axis is negative, area of that triangle above the x-axis is positive. To find the height, I knew my y value was, my x value was 3, so I just plugged into the equation my y value. And remember, that is the answer to my integration from 0 to 3 of 2x minus 5 dx. Calculate. Now this one has the absolute value, so it's a little tougher algebra-wise, but the same concept. Remember the way we do absolute value? 3 minus x, so I go 1, 2, 3. Slope is negative 1. So it's kind of like this. Right, normally we go all the way down, but it's absolute value, so it's in the little v right there. Where does that hit? Well, just set it equal to 0. Hits at 3. my limits are from -1 to 4. So I'm going to go all the way to -1, all the way to 4. In this case, they are both positive. So I'll find all this area. I'll find all that area. And all you gotta do is find the area of both triangles. So to me, 1/2 base times height plus 1/2 base times height. Over here, it goes from -1 to 3. That is 4. Right here again, if you're not really sure how high it goes, just plug in -1. So if I plug -1 into my equation, I get 3 plus 1, so 4. So this one has a width of 4 and a height of 4. Over here, it goes from 3 to 1, so that's only 1. And my height, again, if I'm not sure, plug it into the equation. So that'll be 3 minus 4, which would be -1. Absolute value is 1. So that's only 1. So 1/2, 1 times 1. And I get 8 plus 1/2, or 8.5. Right? That's how you do definite integrals. It's just, graph it, find the area underneath the curve. In this case, we got lucky with the triangle, so it's super easy to do. This one, now you might not be used to seeing this notation right there. That's actually a half circle, which is kind of like this. This is the formula for it. Why? Well, if we go back to a basic circle equation, and then we want to solve for y, get y by itself, we would get y squared equals r squared minus x squared, square root it, y would equal square root. Now remember, it's not, you can't just square root both of them. I hate when people do that. Just keep it the way it is. R squared minus x squared. On math analysis for the win. So that's the half circle equation. All we gotta do is find out what the r is. No, we already know what x is. So in this case, right, r squared based on the formula is 4. So r is 2. So let's just draw it. So basically, when we start at 0, 0, radius is 2, so that would mean to go 2 right, 2 up, left 2. And it's a half circle because it's not plus and minus, right? So if it's plus and minus, it'll be a full circle, but it's just positive. It has to be a function. So you get something to this effect. Now we want the area from 0 to 2, so we only want this part of it, that little quarter circle part. Well, find the area of a circle. That's the area of a quarter circle, so it's going to be 1/4 pi r squared. And then this is 2, and that's 2, so my radius is 2. So I get 1/4 pi times 2 squared, which is 1/4 pi times 4, which is just going to be pi. So that's how it works in general, right? If we want to find a definite integral, and we could draw it, and just draw it and find the area of that function. Good old geometry. Let's have a little shortcut to be using symmetry. So let f be a continuous function on the symmetric interval of -a to a. If f of x is even from -a, then it's just twice that. So what does that mean? Well, kind of like the last one we just did. If it's an even function, like a circle, or x squared, it's not the best drawing of it, or just like absolute value x. If you're going from -a to a, again, not my best drawing on this one, right? Even means go fold in half like a book. If you notice, these two sides match. The area from the left matches the area from the right. The area from the left matches the area from the right. The area from the left matches the area from the right. So it's saying the shortcut, instead of doing the integral of the whole thing, just do the integral of one side and times it by 2. And that's going to be a lot easier because zeros always makes life easier if you use the one side being a 0. So that's all it's saying here, is that the two sides, the left and the right side, are equal because even. Instead of finding the area of the whole thing, which you could, instead you could just do the area of one side. So a little symmetry to help us out. And then what's even more helpful, what if it's an odd function? Remember, odd is when the two sides kind of cancel each other out. So like y equals x is a good example. You get this side and you get this side. Or y equals x cubed is another good example. Kind of like this and like that. And if you're going from negative a to a, notice what happens with these guys. They cancel out. So that's why the integral equals 0. So that's a couple times where we use symmetry to help us out. So let's do one real quick. So much like the exact same one we just did, but now instead of going from 0 to -2, we're going to go from -2 to 2. Well, it's the exact same picture we had before. It's a radius of 2. So 1, 2, 1, 2, 1, 2. I want the whole thing here. So we could integrate from -2 to 2 of this guy. Right, but instead of doing that, I know it's symmetric, so I'm just going to do this side and times it by 2. I'm going to go from 0 to 2. And then times it by 2. So all I got to do is find the area of this guy, which we did last time. If I remember correctly, it was just pi. And then we times it by 2, because we're just going to double that one side instead of the whole thing. And we get 2 pi. Easy enough. So again, if you notice the symmetry, then you can use it to your advantage to make life a little easier. Speaking of things that make life easier, let's talk about the properties of definite integral. These are actually super important. So the first property of definite integrals, so to do this, you have to suppose f and g are integrable over a and b, so they're both integrable functions. Kind of like we did the properties of limits and all the other stuff, same kind of derivatives. Integrals have their own properties. First one is, just kind of like derivatives and limits, you can split it up. If you have two functions being added, you can split them up. So if you can do the integral of this function plus the integral of that function, it's just like taking the integral of each function separately. That's all it's saying. Second one, if you have a constant, you can pull it out. Super beneficial on that one. So for example, if I give you the integral of 3x squared over 5, you could pull out the constant. So in this case, you would pull out the 3/5. It makes life just a little bit easier. And example, the first one's what we do a lot. I should do an example of that one. I don't know, if you have e to the x plus sine of x, you could just split it up. Integral of e to the x plus the integral of sine of x. Next, if you integrate a constant, now these are with limits. I should probably put limits on all these, but it's actually really only important for the next one. So, actually the next few. So if I'm taking my limit from a to b of my constant k, dx, then it equals k times b minus a. So that's just saying, hey, if you're integrating 5 from 0 to 3, that's just going to be 5 times, subtract the limits, 3 minus 0. Which makes life easy. And that actually makes way more sense when you learn a little bit more about different integrals later on. The next one, if you switch the limits, then it's just a negative version of that. So for example, if I'm saying integral from a to b of, I guess a to b already had, let's change that. From 2 to 4 of f of x equals 5. Then that tells you the integral from 4 to 5, 4 to 2, there we go, of f of x equals -5. It's kind of like you're coming backwards. We're supposed to read from left to right, but now we're reading from right to left, so it switches what it is. So if you ever switch the limits, you just make the answer negative. If the limits are the same, the answer is 0. It's essentially saying, hey, what's the limit of a line? Line has no width, so 0. So it's a quick one. Limits are the same, automatically 0. And then last one's probably the most important one. It's kind of it's the transitive property of integration, kind of. So see how this limit here from a to c? If you could break it up. So if you guys stop, if you have say we have a graph like this. This is A and this is C, right? So we're finding all the area underneath there. What this one says is, hey, there's the point in the middle here that you want to break it up. Now you can separate to two separate integrals and add them up. So the integral from A to B plus the integral from B to C is the same thing as this integral from A to C. That's all it's saying. So the key thing here is if you see this, these limits match, that means you kind of combine them like transitive property. You can combine them to be the limits from A to C. That's what that one says. So let's put these properties into action. So here's our example here. I'm going to give you stuff like this, and we're going to use all the properties to get an answer. So they tell us, if you integrate from 2 to 0, it's 2. Integral from 2 to 4 is -3. Integral from 2 to 4 of g of x is 4. These first two were f of x. and an integral from 0 to 1 of f of x is 1. And we want to evaluate these properties. So first one. Now the first thing I do is break it up, use that first rule. So I can split up, so 2 to the 4 of 2f of x minus the integral of 2 to the 4 of g of x. Right, I just split up using that property. Next, now again, a lot of people here see 2 to the 4. A lot of people want to plug in -3 here. It doesn't work like that. This is 2 to the 4 of f of x, not 2 to the 4 of 2f of x. So before I can do anything, I got to pull out that 2. So I'm going to get this. I'll go sideways. 2 integral of 2 to the 4 of f of x dx minus integral of 2 to the 4 g of x dx. Right. Now I could substitute things in. Now I could say, hey, this right here equals this. This is -3. So -6. And this right here equals this is 4. So -4. So I get -10. So that's the way it works. Keep in mind, a lot of people just want to plug in -3 for fx. -3 does not equal f of x. -3 equals the integral from 2 to 4 of f of x. So you have to get that by itself first. It's a very important point. A lot of people just skip that. So that's how that one works. So the next one. 0 to 4. If you notice, I don't have a 0 to 4 anywhere. I have a 0, 0 to 2, and I got 2 to 4. That's the way I'm going to work. So the way I do this is like this. I see where I start. So I know I got to start from 0, and I got to end at 4. Now, do I have anything with f of x that has a 0 on it? Well, this is the only guy. But it's going the wrong. It's 2 to 0, not 0 to 2. So let's flip it. So 0 to 2 f of x. Right? Since I flipped it, it changes this to a negative. When you switch the limits, it makes it a negative. And then I need something with the 4 here, but hopefully it has a 2 at the bottom because I need to connect these. And right, the only way I can connect these two guys is if this guy matches this guy down here. Luckily for us, we have this 2 to 4 f of x. So make this a 2. And I know what that one equals. I end up changing. That's -3. So when I add these together, I get -5. All right, let's do another one of those for practice. These are kind of my favorite things to do. So look at this one. F of x of 1 to 4. Notice I don't have a 1 to 4 anywhere. So I like to start this way. Start with the bottom. 1 f of x. I'm going to have to add it to something, and I want to get to 4. And I might need to add things in between, but let's just kind of go over what I have now. So I need a 1 on the bottom. Well, the only thing with the f of x has a 1 on the bottom is right here. Again, notice how it's switched. It's 1 to 0. 0 to 1. So I'm going to have to flip that to be 1 to 0. And that makes this, since I switched this, I have to switch that, -1. Now I need something to 0 for f of x. Because remember, the next one has to be a 0, right? These two have to match. So it has to be a 0. So with f of x, what has 0 on it? Besides the one we just did. Right here. It goes from 0 to 2. So I have to switch it, make it 0 to 2 instead of 2 to 0. I have to make that a -2. Right, so I switch the limits. I still don't have what I want yet. That ends at 2. I want to end at 4. So I got to add another one. Since I ended at 2, I got to start at 2. And then there's anything that starts at 2. And again, that's 2 0 where to use that one. This one right here, 2 to 4. Exactly what I want. And again, I had to switch that one. That's the way I want it. That's -3. Add them all up, and I get -6. That's the way that stuff's done. Let's move on to talk about comparison theorem. Okay, the comparison theorem. All it says is this. If f of x is less than g of x. So let's say, so this one, f of x should be the smaller one. So this has to be f of x. This has to be g of x. If f of x is less than g of x on a and b. So let's pick an a and b here. Let's say we'll go from 1, that'll be my a, to 4, my b. All it says is, hey, if f of x is less than g of x on that interval, then the integral of f of x must be less than the integral of g of x. Remember, that makes sense. Remember, the integral of f of x is just this guy. That's that area right there. That's definitely smaller than the integral of this guy. Right? So it's higher. So that's a comparison theorem. If you have two functions where one's strictly less than the other one on that interval is the important part. then the integral of the smaller one is going to be less than the integral of the bigger one. Because remember, integration is this area. So if you have area of the smaller one, it's going to be less than the area of the bigger one. So it is. And same with the next comparison theorem. If you have a line m, which is less than the function, which is less than the bigger line m on a, b, then it's saying m of b minus a is less than the integral, which is less than capital M of b minus a. This comes from the fact that m's are just constants. So like this is a small m, this is our capital M. Remember, those are lines. It's like y equals 1 and y equals 5, for example. Yeah, here. So they're just lines. It's like 1 and 5. Remember, the way you integrate it on a closed interval a to b. So let's say we go from 2 to 4. This is my b. All it's saying is, remember the way we integrate it is you just multiply by the difference of the integrals. All it's saying is this, really, that if I integrate this m, that means I'll find the area underneath that m, which is a rectangle. Right? Well, since m is small, that's a small rectangle. Integration of f of x, it's just that curve. So it's going to be this guy. Area into that curve. Well, that's bigger than the rectangle. And if you do the big M, well, the area of that guy is the rectangle from there to there. So that's bigger than all three of them, bigger than the next two. So that's all it's saying. If you have a point like this, then this area is going to be smaller than the area of the curve, which is smaller than the area of the whole thing. That's a comparison theorem. This goes us out real quickly with some assorted multiple choice questions. This gets you guys a feel for it. This first one. Again, these are all from actual AP exams. If f and b are continuous functions, and if x is greater than 0, for all real numbers x, which of the following must be true? So I know which one of these is true. So these are they're just trying to test our knowledge of the properties. So first one says, integral of a, b of f of x, g of x, the same thing as separating them. That sounds like it's true, but it's not. This is right. It's kind of like when you're taking a derivative, right? You do a product rule when you multiply. Same thing here with integration. There's no product rule per se, but it's not just the same thing as simplifying. That's not one of the rules we went over. So that's not true. It's way not true. Right? There's no product. Right? You can never just take a derivative to multiplication or just integrate to multiplication. It's more complicated than that. Second one. Well, when you add, you separate them. Well, that's true. That one's always true. Right? Integration and derivatives are the same way. When you add, or in limits too. Right? When you're adding two functions, you just separate them. It doesn't work like that for multiplication. Only limits do that. But it does work for addition. How about the next one? If you have power on the inside, is it the power of the whole thing? No. That's not one of the rules we went over. It doesn't work that way. So that one's also not true. Now again, it actually might work for some particular functions, but it's not always true. The only one that's always true is all the rules we went over, which is, right, it's separating is probably the most famous one. You can separate if you're adding them. So it's actually only two. You can't just pull a power out. You can't just separate multiplications. You could separate addition though. Next one. If the integral from a to b of f of x dx equals a plus 2b, then the integral of a to b of x plus 5 equals. I love this question. Let's tell you that right now. So we got to use a couple things. First, let's talk about this. So we're integrating a to b f of x plus 5. So first thing I'm going to do is actually separate this. Because I know something about integral of a and b of x, but I don't know the integral of a b of x plus 5, so I got to separate these two. Use the rule we just talked about. So integral of a and b of f of x plus the integral of a and b of 5. So this first one right here, well, I know what this equals. They told me. A plus 2b. This second one, we actually got to integrate. Now that's the rule. Remember the way you integrate a constant is you put a 5 and then you subtract the limits. So b minus a. Now we just do some algebra. Distribute that 5. 5b minus 5a plus a plus 2b. Add like terms. That's not like term. There we go. Those are like terms. And I get negative 4a plus 7b, which is right here. That's a fun one. Okay, last one. If the integral from a to b of x equals 5, and the integral from a to b of g of x equals negative 5, which of the following must be true? Again, must be true. Not can be true, must be true. So let's work with one that's obviously not true. That's this one right here. Right? It's kind of like the opposite we talked about in the first one. You can't just multiply them. It doesn't work that way. No. It doesn't work that way. How about the second one? Could I add them? Yeah, if I add them. Again, that is a rule. If I add them, I get 5 plus -1, which is 4. That one's true. How about the first one? Is f of x greater than g? If f of x is greater than g of x for a to b. So that must be true. Does f of x have to be bigger than g of x? I know f of x is 5 and g of x is negative when I just talked about the whole comparison theorem. But does it have to be true? No. I can think of a counterexample. Let's say I draw a picture like this, where this is f of x, and this is g of x. Right? If I'm taking my limits from, I don't know, 0 to like over here, that's my a and b. Well, a is bigger at some spot, but then it gets less than it, and it starts getting negative. So that's why that's why f is bigger than b is. But f is not always bigger than b, the function itself. So that's why it's not true. Right? The formula we went over is the opposite. It said, hey, this is true, and then what we could talk about it. This is trying to go backwards, and it doesn't work backwards. So that's it. That's the lesson. And we are done.